Hello. I am just getting this figured out. YouTube changed its UI again. But I think these things should be under control now. Looks as though something's going on. So, hey, how you doing? All right. So this is our, I think our sixth stream so far. We're going through a variety of deobfuscation techniques using JavaScript-obfuscator as a base. And now we are actually done with all the JavaScript obfuscator obfuscations. So I'm going to go through in this stream and refactor some of those obfuscations into things that we can reuse more regularly. Because up until this point, it's been largely just ad hoc transformations just to show that deobfuscation is relatively easy. Now we're going to go one step further and just make it trivial. And to do that, I've been working on an evaluator to evaluate JavaScript statically so that we can perform some magic intelligently without us actually doing it. So let's see here. Let's get that hooked up in our latest code. So this evaluator will eventually be open sourced. It's still got a long way to go, but maybe we'll get something out there relatively soon just to show what's going on. It works for what I want it to work for right now. To get it to be a really comprehensive evaluator would take a bit more effort than I really care to put in. So I'm not sure if it's gonna, not sure exactly how far it's gonna go. We'll see. All right, so we have our obfuscated code here. And what I want to do is kill the dead branches that are comparing nothing but literals. So last time we did a substitution for the calls to the B program or the B function, which then resulted in strings from this. And then after that, you got a string literal compared to a string literal, which is a very simple thing to just to replace with a literal Boolean expression. And then you can find dead branches much more easily that way because you just look for the tests in an if statement. And if you have a Boolean there, then you know whether or not it's dead code. So let us first get rid of all these again. So we're going to try to use the evaluator this time. If you joined last time, then you may remember that my evaluator did not work. And that was because I was calling straight .evaluate instead of .evaluate statement. So it was trying to evaluate a single statement as an entire script. It was breaking, and my brain was not working correctly on a stream in order to figure out why that was happening. So now we will hopefully make that better here. So let's see. We need our interpreter. Const interpreter. I've called this thing shift interpreter up until this point. I'm thinking that it's much better to call it shift evaluator or something like that. I don't know. I have not decided on a name yet. So we need our interpreter. Assign it a default context. So now I want to evaluate the first couple statements here because we want to get rid of, or we want to be able to populate these, or we want to evaluate these so that they work properly. And then rather than statically checking out the call expressions here and grabbing the arguments and passing it through our own kind of destringify function, we could actually just evaluate it. Writing the evaluator it was a lot easier than I was expecting to get to the point that I've gotten to so far, because shift scope The scope analyzer for the shift format ASTs does a fantastic job at managing all the variables and scopes that they live. So I don't even actually have to really manage scope in my evaluator, because shift scope already knows where every variable is accessible. So I could just do something like evaluate this, and then jump all the way here and evaluate that, and it'll know that this node is referring to the same variable as this node, and should work. Let's see if it actually does. Otherwise, we'll figure out a different way through this if it doesn't work this time. All right, so interpreter.evaluate. I did fix evaluate, so it'll look for whether or not it's being passed a script, a statement, or an expression, and do what it needs to do. Let's see if it actually works. So AST, first let's get our obfuscated over here. Make sure I am actually going to be passing the correct node. So script statements, yes, the first two statements in our script. Deobfuscate. Evaluate statements 0 and 1. Now, last time we did that, it just broke. Let's see what happens here. No, back to deobfuscating JS stream, stage 6. Node deobfuscate. Cannot find module shift interpreter. npm link shift interpreter. No, come on. All right, well, at least I will debug it here so we can get past this. What is going on? All right, so let's try evaluate statement. Maybe that's the problem. Cannot read property get of undefined. That sucks. See what happens if we evaluate the whole thing. Cannot read property of undefined. Okay, so that means, well, I did not pass it a context that had console in it. So that makes sense. So console, I will pass it our console, and it works. Okay, so the interpreter, so just to go through this. So this is what our original code should run. So it just prints out a bunch of stuff. So that means that evaluate for the entire tree is working, but I'm having a problem with evaluating individual statements. So let's see, shift interpreter. This thing needs a massive refactor. It started as an experiment early in the morning and now has blown up, and it's basically just got two gigantic functions that go through statements and expressions. And I need to make this a lot easier to extend. All right, so I need to look for analyze. So if okay, so I need to analyze manually now. I forgot I did that. Let's get refactor out of here. It's a shift interpreter. So shift analyze AST. Okay, cool. So it works. Well, it doesn't do anything fancy right now, but at least it's not breaking. So that's good. So these two statements should have been evaluated, which means that if we try to evaluate this statement, we should get a return value. Well, let's go through and replace all instances of a call to B with its return value. Okay, so we can get, so that's the variable declarator binding name B. We're renaming that there. We don't really need that. So call expression, call ename B we want. I'm keeping this code down here because I'm going to be copying and pasting some, and it's easier for me to do that if it just exists there. It's kind of sloppy and hacky, but we'll do what we got to do. All right, so we are trying to refactor, replace every call expression that has a name of B. This is a little bit wonky because in minimize code, there might be a bunch of functions that are named B. But in our code, we know what we're working with, so we're dealing with that easily, more simply here. When we start to create more generic replacements for these obfuscations, we'll have to make this a little bit more resilient, but we're not doing that right now. All right, so we have a node, and we are going to get, so if we evaluate those nodes, those are expressions, so we'll need to evaluate expressions for those nodes. We're going to get a Boolean, no, we're going to get a string back. And, well, you know what, let's just see what happens if we just interpret it. Interpreter.evaluate node. Let's see what happens. And now we want to console.log refactor.print. Unexpected string. Okay. That might make sense. So I'm assuming that has to do with this because this will return a string, and this just might not be happy with it. I'm okay with that. So now we need a new shift.literal string expression. Value. Don't need that. It works. That's cool. So the evaluator has evaluated this, evaluated this function expression, assigned it to B, and now has enabled or has run all the call expressions that were referring to this node. It has executed them and then replaced the call expression with the return value. So this is pretty powerful. Like if you remember our code to do this, actually it's right down here. So we need to get the strings out. We needed to, well, we renamed the variable from B to destringify as an example. Then we needed to find the offset within the function. Then we need to find all calls there and then create a new literal string expression and then manually poke our way into the strings list that we have extracted from the AST and then find the value from there. Now, all we're doing is running two statements and then evaluating every call expression node. So this gives us a lot of extra power for free. So now we have expressions like this. So we have two literal string expressions being compared in a binary expression. So what we can do there is, well, let's first grab this source, throw it into our query demo. So what I want to get is all binary expressions that have left. Oh, I was going to try to do a left.type of literal. This sucks. This is actually surprisingly. So one of the benefits of Shift versus another AST format, one of the things that I really like about it is how it separates all literals into their own types. So ES3 and SpiderMonkey AST has a single type literal that can include a Boolean, string, a number, anything like that. And Shift separates them all out into a literal string expression, a literal Boolean expression, literal numeric expression, blah. But now, actually, I'm wishing that I had a generic type for literal so that I could just search for things that have that a binary expression that has a left and a right that is a literal, so we can just compare them. And I'm not sure that I can have partial matches in here. So let's see, GitHub, JS Overson, Shift query. Oh, cool. You can do a regex match. Awesome. All right, cool. Never mind. So I want this to start with literal. See if that works. Nice. So left.type literal and right.type literal. So this will capture all binary expressions that are just comparing two literals. Now this particular match will also capture literal regular expressions, which is not something I really want to grab because I don't really want to compare those. And if I compare them in the evaluator, I'm not sure they're actually going to even compare properly. You know what? I don't even know how you would compare a regular expression anyway. I guess to see if it, you know what? We're taking a detour for a second. Console logs. All right, so I have A equals A, B equals B, A equals B, false. So now if I have A2 equals A equals A2, A equals A. So A, they will be referentially equal. So if we have identifiers that have stored a regular expression, we compare them, compare it to itself, it's going to be able to be strictly equal to itself. And comparing it to even the same type of regular expression still won't get us anything useful. So I'm not actually worried here because I don't think that there is any value in comparing regular expressions. So let's not worry about it. All right, so we have our query here. So refactor.replace binary expressions node. So now here we're going to want to evaluate the entire node and return a Boolean expression, literal Boolean expression value interpreter.evaluate node. See what we get here. And that works. So it has evaluated those string comparisons, those literal comparisons, and has replaced the binary expression with the result of the comparison. So this is something that we could do recursively over and over and over again until we have nothing else to replace, in order to just do sweeping audits of code to figure out where we have branches that are going to be dead. So now we couldn't evaluate a if statement in our interpreter and find much useful for determining the dead code. Well, not the way I'm thinking about it right now, but now that we have gone through and replaced everything, we could, let's grab our code, pb copy, put it into our demo here. So now what we want is if statements that have a test.type equals literal Boolean expression. And now we get all if statements that have a test that is just a literal Boolean expression. So now we can, in our code, test that Boolean expression to determine whether or not we should replace the entire if statement with the consequent or the alternate. So let's see, we have a block statement, so if statement. So we have a consequent, and here we have an alternate down here. So these represent these blocks over here. And now we can just test the literal Boolean expression and determine what to replace it with. So now let's go here, refactor.replace if statement. Test.type equals literal Boolean expression. That gets us all of the stuff that we were just looking at. And now we want to test the test to see what to replace our node with. So test the test. The test will be a literal Boolean expression. The value will just be a proper JavaScript Boolean. So we could just test that. So return, well, I guess it's actually just node.test.value. We can then return the node dot. So if that is true, then we return the consequent. If it is false, then we return the alternate. Need some semicolons because that is how you should write JavaScript. And now we've gotten rid of our dead code. Beautiful. Still have those dumb inner blocks, but those actually don't affect the functionality here. And bam. So this is, I mean, it's not, actually, yeah, it is fairly shorter than what we had here. So let's get rid of all this stuff. So we got rid of the if statements. So we still have the dumb bodies that we can try to get rid of. Let's turn that down. So I remember being dumb when trying to replace the dumb bodies, and I feel like this should be something that is easier, and I don't know why my brain was not working. So let's do that better this time. All right, so let's grab our stuff. All right, so we have block statements. Oh, the problem was because I could not write something that would select the parent because of the way these selectors work. Okay, so it's all right. So body, function body. Method, I have method too. So method will also have a body. So body, function body, so type function body. So function body grabs all of these function bodies. So I could have function body, I want the constructor here. So this is that target, that's not what I want. Constructor. So the function body, wait a second. No, this is the iffy. Console log, hello. Target equals this one. All right, so this is our function body, and we have one statement, and the first statement is a block statement. So I want a function body, or a statement. I'm not sure I can reference indexes in this query language. Let's check it out. Nah, it doesn't work. That stinks. So, oh, it's statements though. So I was wrong there. Block statement. Ah, that works. Oh, that's awesome. All right, so what I can do here, so I want to find function bodies that have a one statement, and that statement is of type block statement. So I want statements dot length equals 1. Cool. Now we grab all function bodies that have this dumb inner block. We have this if statement here, and the if statement has a consequent, and the consequent is what? A block? So it's a block and a block. Let's see here. So expression statement, function expression, body, class declaration, elements, this one, statements. So block statement, block. If statement is right here. So this one right here, so we have a, don't need the test, we have a consequent that is a block statement, and that has a block, and then it has a statement there. So it is a block type, so it is a block statement, has a block type, and that blocks block type, the statements in there as one statement, and that's a block statement. Okay, so wonder if I could actually just capture everything that has a statement and only has one block statement. Will that get me what I'm looking for? Let's try that. So statements.length. Yeah, it worked. Ha! Nice. So now we're just finding every node that has statements has only one statement and has that first statement be a block statement. So now what we can do here is just up-level that block statement, or up-level the statements in that, yeah, replace the node statements with the block statements to get rid of these dumb bodies. So let's see, refactor dot replace. So now this will get us the elements that have statements. Yes, so I need to replace the statements. Actually, I don't need a replacement here because I am modifying them inline for each node. So I was debating, I was actually planning to create a for each method here, but that seemed like something that would be unnecessary or would not be, it would be sugar on top of this. And now that I'm writing it out, it does actually feel like good sugar. You have any opinions? I normally try to avoid much sugar because it's just more crap to maintain. But that was a light annoyance to change that and add something over here. All right, so node statements. So I want node.statements. First one there is going to be a block statement, and out of that, I want its statements. And that should work. Whoops, map of undefined. So node.statements equals, So this was, all right, so cannot read property map of undefined. So node, so the reducer, so something broke in our AST so that it was not operated, it was not structured properly. I could validate it, but how about I just hack around until something works? Console log node. So I'm getting what I want right here. First statement right there. Everything, the first statement out of each is a block statement. Oh, and then I have the block. Forgot. So node.statements.block, then statements. Yeah, sweet. It worked. That's awesome. So we have definitely shortened our code here to get rid of that entire obfuscation technique. So the trivial dead code injection now is, or dead code injection with trivial tests is now extremely easy to bypass just by a bunch of replacements and the evaluating the nodes itself. Sweet. Now for anyone who's following along, we do still have these ugly things up here. We can delete those. So refactor dot delete AST statements. I think I have fixed this so that I can just pass a node to delete. This is an issue last time. Let's see if it was fixed. And it's fixed. Yes. Refactor dot convert computed to static. And bam. So we have this makes me feel much better getting rid of we're dealing with the latest obfuscation we just dealt with, the dead code injection, because a lot of the other code that we had written last time, it was a little bit sensitive, and making it a little bit more resilient would have been a little bit more difficult. There's a lot of little bits there. But now that we've just evaluated stuff, it doesn't really matter how those change. As long as we're finding them correctly, we can just evaluate them and bam, we're good. So that is pretty powerful. So what we can do now is move this to shift refactor, because this is a common thing that might as well run in situations like this. This is very, very generic. We do not need to worry about this being too specific. If we're comparing two literals in a binary expression, then we can evaluate that ourselves, and poof, we will get rid of all those in our code. But that means that we also do have to integrate the interpreter with shift refactor, and that might not be straightforward, because we are going to be modifying the tree with refactor, and we need to have an up-to-date analysis of the tree we're operating on for the interpreter to interpret properly. This is probably going to need a new option for us to deal with. Let's hack it in to start. All right, so let's get back to a shift refactor. We up to date here. ESLint had some security issues in 6.1.0. I just updated that. I do need to make sure that is added properly. Git statute, git pull, up to date. All right, that's good. All right. So I'm going to throw this in util right now. Util is where I'm putting a bunch of the utility functions for shift refactor. As this grows, we'll need to find a better place for it, but I don't know where that's going to be right now. All right, so at the, what should this be called? Reduce Boolean expression or reduce binary expression? I can live with that. I don't have my shortcuts. Sonny did recommend a VS Code syncing plugin, but I clearly did not install that. All right, so we have a reduced binary expression. We want to have a binary expression. So you'll also notice, if you're paying attention, I'm writing the test first because I am more often than not somebody who does the test-driven development style of development, because I feel like it gives me the opportunity to form hypotheses about my code before I write the code to prove whether or not my hypothesis was correct. So right now I need to figure out what I'm going to be testing, and then I need to write the code that will figure out whether or not it works. So we want a Boolean expression, which we can do pretty easily. So A equals B, and we want that to be reduced to a true. So down here, we want this after we've run our reduce binary expression. We want that to equal true. And now this should fail. npm run test, refactor.reduce binary expression is not a function. Now, obviously it's not a function. For people that I work with who have never worked in a TDD, test-driven development style workflow, it looks stupid at the start. Like I'm testing something that clearly doesn't exist. Strict TDD is to really just test that function can be called and then make that function exist and then test the implementation. This is skipping a few steps because I think that level of TDD strictness is stupid. But now we have our test and we can start to flesh it out and then run our test as we go to see whether or not our hypothesis is proving to be correct. All right, so we have our util functions here. We want to reduce binary expression. So this, we're going to want it to recursively replace, but we are not testing recursiveness yet. So let's leave that on the table for now. We will need our interpreter. So to link it, npm link shift interpreter. All right, so actually we need it up here. So const interpreter equals require. I feel like that should be auto-completing. This is not written in TypeScript, and the interpreter I did write in TypeScript. I miss TypeScript so much. every time I'm not writing in it. Like, I love JavaScript. I have no problem with it. But if I've been writing a lot of TypeScript and then I jump back to JavaScript, it bugs me that not the IDE is not doing enough for me. So if you have, that's another thing. If you haven't tried TypeScript, it is beautiful. I was never a type fan. I loved Perl, Ruby, JavaScript, and just didn't really care that much about types. And then I jumped into TypeScript late last year, and it is freaking phenomenal. So that is a recommendation to jump out of this and try TypeScript if you have not done that yet. All right, so we want to replace all literals, binary expressions that have literals on both sides. We want to return. We want to replace them with a Boolean expression. So this actually, we're going to need to create our interpreter and analyze the AST that we currently have in order to interpret this. And that is not going to be a very performant thing to do too often. So this is certainly something that's going to need to be optimized for any amount of code that is larger than the small little contrived bit we have. But we'll deal with performance improvements some later time. So const interpreter equals new interpreter. And now we need to interpreter.analyze this.ast, which should be what I've called the AST. So now we have the interpreter, and we want to evaluate that node. That should give us what we're looking for. Let's run our test. Invalid return type from replacement. Function undefined. I'm not returning everything because I have this here. Cool. Okay, so our test ran, and our test is clearly wrong. Well, something is wrong somewhere. So it's expecting false. Give it a value of true. Where is our test? util.test. So yes, this is the test that is broken. A should not equal to B, so this should actually be false. Now we can run our test again, and it works. Now we want to make sure that we recursively reduce these. So I'm just going to add a new test here so that they are separated so we get better output in the logs. So A equals B. A equals is this going to work? This is not what I'm going to want. Is it? Yeah. Actually, what will this do? So C equals A is false, A equals false is false. That's how it works, right? I don't know. All right, well, whatever, it's a test. So we want this to equal false. So this will be a binary expression with the left of a literal string expression and a right of another binary expression. So the binary expression here will be replaced first, and then what we'll have here is a literal string expression compared to a literal Boolean expression, which should then be reduced if we have set this up properly. It hasn't been set up properly in this particular implementation, but now we've written a test that will fail. Now we can see it fail. Now, we should assert that it's failing the way that we want it to fail, so that we have more confidence that our test is right. Whatever. We'll live without that for now. All right, so we want to replace recursive, which actually should just work automatically. Bam. Done. All right, so now we have our an updated shift refactor. Let's link this, go to our deobfuscating streams, and then further simplify our code. So now we are linked to our local shift refactor. Go back to deobfuscating streams. So now we can reduce binary expressions. So let's check out our deobfuscation. No, cannot find module shift interpreter. That's because you have unlinked yourself. This is something that ends up being kind of a problem for me dealing with npm linking, is that every time I do link something else or do an npm install, it resets it. I have not actually been bothered enough to research how to fix it. So if you know how to fix it, then please let me know, because it is kind of annoying. So shift refactor is complaining about shift interpreter. npm link. Oh, because I have to do this again. So it is getting close to annoying me enough to fix this. Not quite yet though. Cool. Well, I mean, it still works. Our code has already removed the dead branches in the if statements. Actually, let's get rid of those so we can see it. So our reduced binary expression has reduced things to binary expressions. So we have further reduced how complicated our code needs to be to deobfuscate the dead branches. So now we could extract this too. Remove obviously dead branches. It's gonna be hard to call something remove dead branches because I don't want to have that function do much evaluation on the test. I want the evaluation to have been pre-done, so all we're left with is a simple Boolean expression. That's fine, right? All right, so util over here. Oh, we're shift interpreter still. Shift refactor. So util.test. And I want to remove dead if statements. I think this is going to be that is too loaded of a method name. So this is a very, very loose interpretation of a dead statement. Although we could just expand it. We could expand it over time so that it just removes whatever it can consider dead. Yeah, that's not that bad. So we're gonna call this remove dead if statements, and its functionality will improve over time as we become more intelligent at determining what is dead. Now, in a situation like that, dealing with semver, major minor patch, if I modified the behavior of this function, of this method, so that it removed more than it used to, but the function call stays the same, would that be a major version update? What do you think? Should remove if statements with simple Boolean tests. So if true console.log whatever, else console.log b. So we should expect that we get out of this console log a. Ooh, you know what it's gonna do though is it's gonna leave us with that dumb block. Should we optimize those in the remove dead if statements? Probably, because they're ugly and they bug the crap out of me. It's all right, we'll deal with that. Remove dead if statements. Let's check our tests. Remove dead if statements is not a function. Makes sense. So reduce binary expression. Remove dead if statements. So we have our interpreter, we have an analyze. We want to get if statements that have a literal Boolean expression. And then we want to replace it with the, So this is replacing the entire statement with that. We can't replace it with a list of statements. That actually might be a good feature to have for a place going forward. If we have a single statement and we replace it with a list of statements to just kind of shove those statements in the place of that last statement, I don't know what other complications that might introduce, so I'm not going to do it right now, but I'll think about it. All right, so we don't, what am I doing here? Oh yeah, that's code left over because I'm copying and pasting. So now we get the consequent or the alternate. So this should do something, but it's going to give us that block. So we need to get rid of those block statements. And you know what? We can do that generically too. So this dot query, looking for everything, everything that has what we just talked about. So it has has only one statement, and that one statement is a block statement. So we just shove those statements back into the parent statements. And now we get that. That works perfectly fine. So now let's go over here, and now we can get rid of both these. Refactor dot remove dead if statements. No deobfuscate. We're getting simpler and simpler. So this one is not going to be easy to generalize because this is something specific to this. Although we could just have a generic function in shift refactor that just calls the call expressions. So that'll assume that you have already, but you would need to have that particular interpreter. The relationship between shift refactor and the interpreter is going to be a tough one, because if we've modified the tree, well, that's not a very good example of modifying a tree, but if we have a lot of work being done here between a call to interpreter, then we're going to have a messed up tree to work with, and that's not going to give us what we expect. So I'm not comfortable in abstracting away the interpreter that far yet. It's definitely something I would like to do and something that sounds valuable. I just don't know how to do it yet. So we'll leave that. All right, let's see. We are golden here. What else do we want to do? Yeah, I'm pretty happy with where that has gotten. I can't publish shift refactor yet because shift interpreter has not been published yet. I'll go through the process of cleaning that up and getting that publishable at some point. That's a bit of work. I'll go over a bit of shift refactor, shift interpreter, and actually see what else we can implement. So let's see here. So the tests here are pretty basic. These are not testing a tremendous amount of JavaScript behavior, and it is delegating a lot of the more intricate behavior to the environment that we're running in. So we're leveraging the host environment to operate the way JavaScript should operate because we're writing it in JavaScript and evaluating JavaScript. That allows the interpreter to be much simpler than it would otherwise, and it allows me to cut a lot of corners and not necessarily worry about exactly what the spec says. Let's see, so we have object member assignment. We've done that. So the way that I'm testing this also is just asserting that code will result in the same execution value in the interpreter as it does when evaling. So this is evaled, and we get the execution result here at the end, which is the B property of A. So in an eval, that would give us 2. Interpreter should also give us 2. To make sure we're running with a good setup here. Cool. All right, what else do I need to test? So classes, classes are ugly. I have cut a lot of corners with classes, and I feel as though the effort I'm going to need to make in order to put classes over the top is going to be substantial, and I'm not sure that I really care enough about that yet. Let's see. I think I know how to break it right now. So should allow for, So the problem is when I create a class and I go through and I create the intermediate objects, I create intermediate functions for all function types. So function declarations, function expressions, methods. I also have an arrow functions down here. Now the problem there is that the constructor, the call to super is abstracted out of the actual method, and I think that's going to mess everything up. And I don't know how to fix that right now. So I'm going to avoid that because that is easily something that I will be comfortable procrastinating for as long as humanly possible. So let's try a different scenario. Ooh, let's try binding. Bound functions, because I think this is going to break too. So functions should be bindable to arbitrary contexts. So let's see here. So A equals function. So let's return B plus this dot A. So so bind A equals 10. So I've got, this is gonna be confusing. So we're taking a param, we're adding it to whatever we have on our context. So we're going to bind that with a context here, and then we're going to call A. Now this, an A with a variable of 5, so this should give us 15, right? A is not defined. It's because I need to declare it. Cannot execute non-function. Cool. So that is not the error I was expecting. Yeah, that's interesting. Oh, that's because bind is being called on what ends up being an object here. And that is going to be strange. I'm going to regret a lot of my choices hacking through this evaluator. Okay. So what I'm going to need to do is probably special case function prototype methods in order to have them work properly on the intermediate function type. All right. That is going to be more work than I can do certainly in 5 minutes. So we're going to have to hold off on that. But thank you very much for joining. I appreciate it. And this is a fun process for me. If you have any questions on JavaScript, how to manipulate JavaScript, transform JavaScript, reverse JavaScript, do any sort of weird things with JavaScript, especially with like things like the shift AST, shift query, shift refactor, stuff like that, please reach out to me, because I just like talking about this stuff and I like doing it. So Twitter is the best way to get in touch with me. It's at JSOberson. Feel free to reach out anytime. All right. See you later. Thank you very much, and goodbye.